For today's lesson, we are going to be focusing on the law of sines. So your objectives for today are that students will be able to derive the law of sines and use it to solve triangles using angle, angle, side, angle, and the ambiguous case, side, side angle. All right, in our activator, we looked at a question about solving non-right triangles. And it's that question that drives us into needing something like the law of sines. The law of sines is something that we will use to help us for solving these non-right triangles. So in our instructional focus, we'll look at how that law is derived. We'll look at how to use it to solve triangles, and then we'll look at what we call the ambiguous case. All right. Once we've done that, we'll take a look at some of the applications of the law of sines. So the derivation of the law of sines will come from the two triangles in the figure on the right-hand side. This kind of covers our bases in terms of the different types of triangles we might see that are non-90 degree triangles. The triangle on top is an acute triangle, meaning all angles measure less than 90 degrees, and the triangle on bottom is an obtuse triangle, meaning that it has one angle, in particular in this case angle B, which is greater than 90 degrees. We've drawn an altitude dropping down so we can have a 90 degree triangle in our graphic, so we can use that triangle, the 90 degree triangle, to find some values for the sine of an angle. So in the acute triangle on top, first off, we know that in either triangle, actually, the sine of A, right, the sine of angle A is going to be that altitude, h, divided by the hypotenuse b. So sine of A is h over b. And this is actually true in both triangles because our 90 degree triangle is the exact same in both of those instances. So that's the first one. We know sine of A is equal to h over b. The sine of angle B on the left, all right, or on the top triangle, is just simply the opposite side, which is h, divided by the hypotenuse of that small triangle, which is a, or h over a. So on our acute triangle, we get sine b is h over a. In the obtuse triangle, when we want to get the sine of angle b, we just want to use this little angle here, which is just going to be pi minus b, or 180 minus b, right? So when we deal with sine or cosine, we're always talking in terms of radians. That's why we do pi minus b. And that would give us that smaller angle, which would give us h over a. But we also know that sine of pi minus b is just sine b. We learned that in a previous lesson, meaning that sine of pi minus b is h over a, or sine of b is also h over a. So notice we got the same thing for both triangles. In both cases, sine of a is h over b, and sine of b is h over a. All right, so solving for h in both equations, right? I could get in the first one, I could get h is equal to b sine a, and I could get that h is equal to a sine b. All right, I know that that's going to be true in both cases. Now, and it's not a capital A there, I apologize. It's going to be a lowercase a sine b. We use lowercase because that's the side length, which then if we set those equal to each other, b times the sine of a equals a times the sine of b, the fun thing we can do now is I can divide everything by ab. On the right, the a's cancel. On the left, the b's cancel. And you end up with this rule. Sine of a divided by a is equal to sine of b divided by b. We could do the exact same thing with a separate altitude if we turn the triangles to figure this out for side C, and we end up getting that sine b over b equals sine c over c, or sine of a over a is going to be equal to the sine of b over b, which is equal to the sine of c over c. And this is true for all triangles, whether they are a right triangle or not. And this is a great thing here because now all of a sudden we have a rule that will allow us to solve for missing values in triangles that are not right triangles, that don't have a 90 degree angle. So simply put, in any triangle ABC with angles A, B, and C, and the opposite sides are lowercase a, lowercase b, and lowercase c respectively, the following equation will always hold true, that sine of a over a is equal to the sine of b over b, which is equal to the sine of c over c. So now we can use that law of sines to solve a triangle given two angles and a side. So we're given the triangle drawn at the bottom of the screen. The description is just angle A is 36, angle B is 48, and angle A equals 8, which is the drawing that we have down at the bottom. And I want to know, how could I solve this triangle? And when I say solve the triangle, what I'm saying is we need to find the missing angles and sides. Well, angle C is the easiest thing for us to solve for. That's where I would begin because I know that the sum of all angles in a triangle is 180 degrees. So to find angle C is just going to be 180 minus 36 minus 48. And that will give us the measure of angle C. So 36 and 48 gives us 84. So we get that angle C is 96 degrees. So that's the first thing that I find is angle C being 96 degrees. Now that we have that, we can go ahead and we can solve for the different sides because I know that I could say that the sine of angle A, which is 36, divided by side A, which is 8, is going to equal, for example, the sine of 48 degrees, and these are degrees, right, not radians. The sine of 48 degrees, let me fix that 8 so it's easier to read. The sine of 48 degrees divided by side B. All right, now if I want to solve for side B, I would multiply both sides by 8b, all right, and that's going to get rid of the 8 and the b. So I would have b sine 36 degrees is equal to 8 sine 48 degrees. Then I would divide both sides by sine of 36. All right, which would give us the value for B. Now we would need to plug this into a calculator. When you do that, you want to make sure that your calculator is in degree mode. All right, and I'm just going to quickly go and type this into my calculator that I have sitting in front of me. But you would just make sure your calculator is in degree mode, and you would just do 8 times the sine of 48 degrees, which gives you about 5.95, and you would divide that by the sine of 36 degrees, which gives me a value of about 10.1. So B is equal to approximately 10.1, and we don't have units, so it would just be 10.1 units. We would do the same thing to find side C. We would set up the exact same equation, and we would end up with just C is going to equal 8 times sine 96 divided by the sine of 36. It just kind of works out the exact same way as the previous problem. And you would type that into your calculator, 8 sine 96. We found before that, and then divided by sine 36. It's the exact same process as what we did before, and we get that to be about 13.5. So C would be about 13.5. Now, if you're trying to think about this in just common sense terms, knowing that angle A, right, is the smallest angle and its opposite side had a value of 8, well, angle B is a little bit larger, so side B should be a little bit larger, which 10.1 is a little bit larger than 8. Side C is the biggest angle, 96 degrees, so it should have the biggest side opposite, so C should be even bigger than that, which it is. These, I always want to ask myself, does the answer make sense in the context of the problem? And in this case, it definitely does. All right, and if we look at the solution given from the text, we end up with the exact same values. We followed the same process and got the same results. So using the law of sines, we're able to solve all of the different sides, and same thing as that angle. What we did first to find that missing angle is the same thing that they did first as well.
Let's solve another triangle where we're given two sides and an angle. And once again, we're going to use the law of sines. So if we have triangle ABC where side A is 7, B is 6, and angle A is 26.3 degrees, as can be seen down in the figure below, go ahead and attempt to solve this problem. Take a couple minutes, see if you can set up the law of sines such that you will be able to solve the rest of the triangle. Take a few minutes, see how you do. All right, welcome back. You should have taken the time to attempt this problem. I'm going to now talk about how I would go about doing this. Well, I know that angle A corresponds with the side across from it, which is 7. That's side A. And angle B is going to match up with side 6. So I can solve for angle B right off the bat. I know that sine A, sine of angle A, or sine of 26.3, divided by sine A, which is 7, is going to equal sine of B divided by side B, which is 6. So I can multiply both sides by 6, and I get 6 sine 26.3 divided by 7 is going to give me the sine of B. So once again, make sure that your calculator is in degree mode, and you're just going to type in what we have there, 6 times the sine of 26.3 degrees, and you're going to divide that by 7, and you'll get this value 0.379, and there's more decimals after that, but essentially 0.379 is equal to sine of B. So now if I want to find angle B, I would do the inverse sine, right? We're going to now use that inverse sine that we used previously of that decimal value to get the measure of angle B. So I do inverse sine, and I get that angle B is going to equal 22.3 degrees. Now that I have that, I can easily find angle C, because angle C is just going to equal, the measure of angle C is going to be 180 minus 26.3 minus 22.3. All right, and I do that, 180 minus 26.3 minus 22.3, and I find that angle C is equal to 131.4 degrees. So now that I have this, I can go ahead and set up my law of sines again. We can say sine of 26.3 over 7 is equal to sine of 131.4 over C. And if we do our cross multiplying and dividing, we find that C is going to equal 7 times the sine of 131.4 divided by the sine of 26.3. So we type that into our calculator. 7 sine 131.4 gives me about 5.25. I divide that by the sine of 26.3. And I find that side C is going to equal about 11.85. So now we've solved the triangle. In the solution that we get from the text, that's exactly what they do, is they solve for angle B, they get angle C, and they go through, I said 11.85, they rounded it to 11.9, but we were able to solve the entire triangle, and we got all 6 parts. Now, it just so happens that the law of sines isn't quite enough in certain instances. Sometimes we have what we call the ambiguous case. And the ambiguous case is this. What if we know that angle A is 30 degrees and that side A is 6 and side B is 7? Well, in this case, because side A is shorter than side B, we could potentially have 2 different triangles. We could have the triangle on top or the triangle on bottom. Both triangles are valid given those sides, right? This is why back in geometry, when you were learning triangle congruence, why side-side angle was not enough to prove triangle congruence. This was that case where it didn't work. Well, if we have this ambiguous case, what do we do? And the answer is you would solve for both cases. We're actually going to have to try and solve the triangle in 2 ways. All right? And we'll just take a look at the solution from the text in this one instead of going through it bit by bit. But we can find that as we go through, we can determine the value for sine of B and get that angle B has to be 35.7 degrees. Now, the issue there is angle B could potentially be an obtuse angle, right? And because of that, we could find, well, what would that angle be in the other quadrant, what's the other value we could have gotten from doing this? And we could just say 180 minus 35.7, which we see on the right. So angle B is either going to be 35.7 degrees or 144.3 degrees. In both cases, this will work, and we'll find that angle C then might be 5.7 degrees, or angle C is 114.3. Either of these values will work. All right? And then in doing so, we have to go through and solve the rest of the triangle. But because of this ambiguous case, we could get the solution that's seen here that I just circled, where we have all three angles and all three sides, or we could get the one at the bottom, where notice angles B and C are different, which means side C is different. Side C ends up being almost 11 or almost just 1. So a very, very large difference can be noticed as a result of that ambiguous case. So we need to be aware of what could potentially happen as we solve triangles using the law of sines. So now that we know a little bit about the law of sines and how it can be used, we can now apply it to other problems. So for example, here's a problem that is called locating a fire. And in the situation we have Forest Ranger Chris Johnson is at Ranger Station A. All right, and they spot that there's a fire out in the direction 32 degrees east of north, meaning the angle between north and the fire is 32 degrees as seen in the diagram on the left-hand side. Ranger Rick Thorpe at Ranger Station B on the other side, all right, he sees the same fire on a line 48 degrees west of north. And there's 10 miles between Ranger Stations A and B. And we want to know the distance from each Ranger Station to the fire. So we could actually now draw a triangle based on this, knowing the angles, and we could actually solve this triangle and figure out the values for A and B. And the way in which we would go about doing this is, once again, by using the law of sines. If we take a look at our triangle that's formed, we know that this angle A of the triangle, is going to be 58 degrees because these are complementary angles, meaning they add to 90. And on the other side, angle B is going to be 42 degrees. And I know that angle C then, all right, is going to be 80 degrees because it's a triangle. All right? So we're given this. We know this. We have our triangle all worked out. So I could now say sine of angle C, which is 80, divided by 10, is equal to sine of angle A, sine of 58 degrees, over A. And that will tell me the distance from Ranger Station B to the fire. And I could set up the same thing, sine 80 over 10 is equal to sine 42 all over side B. We could solve for the variables and then solve for the distances. As we can see here, this is exactly what it gets set up in the book solution, and in doing so, we can follow the solution here and find that A will give us 8.6 miles and B will give us 6.8 miles. So in this lesson, we developed a means for solving non-right triangles. We derived the law of sines using our understandings of just basic trigonometry, and then we used the law of sines to solve simple non-right triangles that involved angle-angle-side or angle-side-angle, and then the more difficult side-side angle scenario in which we had that ambiguous case, or the potential for the ambiguous case. Finally, we use the law of sines to solve real-world applications. So you should be able to derive the law of sines and apply it to different types of non-right triangles, and you should be able to utilize that in solving real-world problems that would use the law of sines.